Hi, today we'll discuss how to graph rational equations. I hope that by the end of this video, you'll be able to accurately represent the complexities of rational expressions in graphical form. Thanks for coming to Fremont Math Hub. Well, what are rational expressions? For a reminder, these expressions are fractions where the numerator and denominator are polynomials. You can't graph these without knowing and understanding what it is that they are. So here's another way of putting it. You can think of it also as a ratio of two polynomials. They can be very simple. They can also be very complex. A polynomial is going to be anything that contains a variable and or whole numbers within. So a mix of those in the numerator and denominator. This is a simple one. 2 over x. We just have one variable on the bottom and we have a whole number up on top. Okay, a little more complicated. Have a polynomial on the bottom and a whole number on the top. But what about this here? This one is objectively much more complex. You have two of the more traditional polynomials on the top and on the bottom. Okay, here's an example of what a rational expression or rational equation graph would look like. Often they have these weird shapes, and they look like they are not touching or barely touching a certain part of the graph. And the reason why is based on a series of parts of these graphs, which we'll go into. One being right here. Take a look at this red dotted line. Note how the arrows on both ends are not touching this line at all. Now we know this to be the y-axis, right? But this is also known as an asymptote, a vertical asymptote to be exact. How do you know it's vertical? Well, it's moving up and down. Okay. On the other hand, there aren't only vertical asymptotes, there are also asymptotes that look like this. In this case, this is represented by the x-axis, and this is known as a horizontal asymptote. So these are just things, again, where the graph will get extremely, extremely close to, but never really touch. Now, note also, and this isn't exclusive or unique exactly to rational expressions or equations, but to graphs in general. Usually you have an x-intercept or multiple and a y-intercept or multiple. But if you look here, neither of the blue lines are touching the x-axis or y-axis, and that's okay in this case because they're asymptotes. In fact, the x and y-axis are the asymptotes of this equation. Now, let's talk a little bit more about vertical asymptotes. How do we figure out what these are? Well, a vertical asymptote, it'll have the equation x equals a, where a is some number, some whole number, maybe a fraction even, maybe a decimal. And it only exists if, as the graph approaches this line, it increases and or decreases, but with no limit. So this is just a more technical way of saying that the graph will never touch this invisible, or dotted, as I showed you before, line. So the way that you find out what your vertical asymptotes for a rational equation are is take the expression and set the denominator equal to 0 and solve for x. Okay, you could have 1, you could have 2, you could have 0 asymptotes. It'll depend from expression to expression. Now, here's something super, super, super key. Don't just solve for the denominator and set it equal to 0. You want to double check that the answers it is that you got, whether you have multiple or just one, that when you plug them into the numerator, if your numerator has a variable like x, okay, that it doesn't make the numerator equal to 0. If it does, then it's not a valid vertical asymptote. It doesn't count, okay? So here are some examples. How can we solve for the vertical asymptote here? Let's think about it. Okay, let's start with the one on the left. So again, we're going to set the denominator equal to 0 and solve for x. And in this case, it's going to be pretty simple. Just set x, or our denominator, equal to 0. So what does that mean? Well, x equals 0 is our potential, and that's the key, potential vertical asymptote. There's one more thing we have to do. We have to check that it doesn't make our equation, or our expression in this case, invalid. So does our numerator have an x that we can plug in 0 into? Not really, not in this case. So that means that x equals 0 works. It is a vertical asymptote. You can't even plug it in to the numerator. Okay, let's try the right side. Okay, so this one's a little more complicated. We're setting this whole polynomial equal to 0. Now, if you remember how to solve quadratic equations like this, where you have x squared, an x squared equation, you can factor or you can do quadratic formula. Factoring usually will be easier as long as you remember the different forms of factoring. If you use the AM method, aka the method where you find two numbers that are going to add up to, okay, add up to the number that's here, in this case, which is 1, but they also have to multiply to -2. Well, think about it. What two numbers multiply to -2 and at the same time add up to 1? Are there any two numbers that do that? Yeah, actually, there are. +2 and -1. 2 and -1, add them up, it's 1, multiply them, it's -2. If you didn't know that, then you could use quadratic formula to solve for the two numbers. Okay, so you set these two equal to 0, and then you do something called teeing off, where you can draw a letter T and separate these two like this. I'm just going to draw one of these. You set each of the parts equal to 0. So you'll have it like this. And then when you solve for 0, you'll end up with x is equal to -2 and x is equal to +1. So what does that mean? These are our potential vertical asymptotes, but you want to check. Plug in both of these into your numerator and see if it ends up working. Make sure that the numerator does not end up equaling 0 when you plug these in. So let's try it. Plug in -2, you get -11. So that's good. What about plugging in the number 1? Plug that in. 5 times 1 is 5. 5 minus 1 is 4. You're good. That doesn't equal 0. Okay, so those are our two vertical asymptotes. Okay, now we're going to talk about the horizontal asymptotes. So these are a little bit more involved in terms of how to find these, but the definition is pretty similar. The equation for a vertical asymptote is x equals some number. Well, for a horizontal, it's y equals some number, a fraction, a whole number, an integer, a decimal. It only exists again if as the graph approaches, it increases and or decreases. There's no limit. It never touches this invisible line. So, pay attention to the terminology here. If you have a polynomial on top and on the bottom, the degrees, okay, this is a very important term, the degree of the numerator and denominator, we're going to call n for numerator and m for the denominator, okay? Or you could say d, whatever letters, it doesn't matter. The degree is going to be the highest exponent that you see on the top and the highest exponent that you see on the bottom, okay? Compare across the two. If the degree of the numerator is less than the degree of the denominator, then the asymptote is the x-axis. That means that your equation ends up being this right here, y equals 0. Y equals 0 is also known as the x-axis. Okay, next case that I already have here. If the two equal each other, okay, this is the more complicated case. If your degrees are the same, then your asymptote is going to equal C divided by D. C is the coefficient. It'll be next to the x term that has the highest exponent in the numerator, and D will be the coefficient of the x term that has the highest exponent in the denominator. Okay, divide those, and you'll get your asymptote. Y equals some number or some fraction. In the case where you're top heavy, okay, that's one way to remember. If your top degree is greater than your bottom degree, there's no such thing. There is no horizontal asymptote at all. In fact, in this case, you may have something called a slant asymptote. Okay, so let's try it. Let's try it. Starting with the one on the left. Degrees of the numerator and denominator. Well, at the top, there's no x term. So what does that mean? Well, it's implied when you don't see an x term that your x term is also known as x to the 0. X to the 0. Anything to the 0 exponent equals 1. So you can say that. Therefore, n would be equal to 0. For your denominator, it's x plus 1. Well, what's our degree? The highest exponent there, you don't see it, but it's implied to be 1. It's x to the 1 power. So d, or m, is equal to 1. Okay, now we want to compare them, n and m. Is n less than, greater than, or equal to m? Well, n is less than m. 0 is smaller than 1. So that means, well, what's our rule? When n is less than m, the x-axis is our horizontal asymptote, aka y equals 0. Okay, let's try the right side. Our numerator is 5x squared. Our degree is 2. Okay, so n equals 2. For our denominator, our greatest exponent is 2 also. Okay, what does that mean? Well, our n and our m are equal to each other. So this is the special case in which we have to do an extra step to figure out our asymptote. We have to compare the coefficients, the numbers that are being multiplied by these variables with the degrees. So we're going to do 5 divided by 1. That means our asymptote, horizontal asymptote, is y equals 5. Okay, the other part of graphing these equations, that's super important, x and y intercepts. Again, this isn't only for these kinds of equations, it's for all equations. Okay, in the case where you do have x and y intercepts, the way it is that you find out is like this. For x, set the numerator equal to 0 and solve for x. okay? Now, if you remember, when we were trying to figure out the vertical asymptotes, the way that we checked to make sure that they were valid is by plugging in the answer into the numerator and seeing if it made the numerator 0. Then it wasn't a vertical asymptote. It's the same thing here except the opposite. To find the x-intercept, we're setting the numerator equal to 0. So we also want to make sure that whatever answer that we get, that it doesn't make the denominator equal 0. Okay, then it doesn't work. It's not an x-intercept. Okay. For y-intercept, we're going to set x, all the x variables in the equation equal to 0, and we'll solve for y. Okay, and I'll show you how to do this here with this example. Okay, so we're going to go through each one here. For y equals 5x squared over x squared plus 1. Okay, this is an example that we just talked about. The asymptotes we have discussed as being, for one, horizontal asymptote, that was y equals 5. Okay, now let's talk a little bit more about the vertical asymptote. For the vertical asymptote, which we just talked about here, we set the denominator equal to 0. When I do that, I can move the plus 1 to the right side, so I'll have x squared equals negative 1. To solve this, I would take the square root of both sides. When I do that, anything in which I have a square root where there's a negative number underneath it, that's not valid. That's an imaginary number. It doesn't work. Therefore, there are no vertical asymptotes at all. Okay? Step 2, we're going to look for x and y intercepts, if this graph has them at all. X-intercept, set the numerator equal to 0. Okay? When we do that, we get x equals 0. Okay? Does this work? It works because the denominator isn't made equal to 0 when we plug it in. Okay? Now, down here is the y-intercept. We set all the x variables in this equation equal to 0. So we plug in 0. 5 times 0 squared over 0 squared plus 1. You'll get 0 divided by 1, which is just 0. So our y-intercept then is y equals 0. Okay, so that means then that what we're doing here is we have an intercept at x equals 0, which is, well, here, and y-intercept, well, here. So that means that we are touching the origin. We're touching the origin here. Okay, that's one. And then we also know what the horizontal asymptote is. Okay, but that's not enough to draw a graph. The other thing it is that you want to do is plug in random x values into our equation and solve for them. So you want to get a full graph. So choose maybe 2 numbers that are negative, 2 numbers or so that are positive. Okay. It'll also depend on what your asymptotes are. If you have vertical asymptotes, let's say that we had a vertical asymptote here at x equals negative 3 and an asymptote here at x equals, though it's a bit unclear, x equals 3. I would want to plug in maybe x equals negative 4. I would want to make sure that I cover this section here in the middle. So maybe I'd plug in, this is negative 2 and maybe positive 2. And then over here, I'd want to make sure that I get this section covered. So I would plug in something after 3. Hopefully that makes sense. Whatever it is that I plug in for x, I want to make sure that it's enough for me to draw a graph that makes sense. Okay, so I chose -5, -3, 1, 3, and 5. And you can check this on your own with the calculator or by hand. When I plug in each of these values, these are the coordinates it is that I get here at the bottom. I get some with decimals here, and I don't round up, I just keep the exact decimal. Okay, so let's put this together. Let's do it. Right here is our horizontal asymptote, which was y equals 5. Okay, so I just put a straight line through y equals 5. There's my x-intercept and y-intercept. It's right there at the origin. Okay, right at the origin, right there. Now again, if I just stopped here and I didn't plug in x values, I wouldn't know how to draw this graph. It could look like anything. That's why we choose values. So now I plot each of the points. Okay, -5 and 4.8, -3, 4.5, 1, 2.5, 3, 4.5, 5, 4.8. Okay, well, what does this look like here? I'm going through the origin. I'm also going through those points. And I want to make sure that I get really, really, really close to the horizontal asymptote, but that I never touch it. Well, what will that look like? It looks something like this. Just imagine that there are arrows on the left and right side. They're getting closer and closer and closer to that red line, but never actually touching it. This is what this graph would look like. Okay. I hope that by explaining how to work with these rational equations, asymptotes, x and y-intercepts, as well as plugging in needed x values, that you better understand how to represent these rational equations in a graph. Thank you for your time.